Hello, welcome back to another video from my series on the effect, my book on the Introduction to Research Design and Causality. Now, in this video, we're going to be talking about theoretical distribution. Because remember, our entire goal here, right? The entire goal of doing all this research in the first place is that we want to understand something about how the world works. Now, inconveniently, we don't have the world, we just have our data. But that is the goal of what we are doing, and the goal of most of statistics, honestly, or inferential statistics in any case, before anybody gets mad at me in the comments, is that we want to use the data that we have to learn something about the broader world. You can call it the population, you can call it the data generating process, whatever it is that we want to learn something about, we want to use the data that we have, which is only one little window into that world, to learn about the world more generally. That's what we are trying to do. It's our goal. So how can we do that? How can we use the data that we have, which is imperfect and incomplete, to learn about the entire world? Tall order. So a good way to start thinking about this is to realize that the world has some sort of truth to it. We need to believe that. We need to have some idea that there is some sort of truth in the world. And then the idea that we're going to take is this. We are going to say, okay, the world has some sort of truth to it. And that includes things like, what is the effect of X on Y? What is the average of this variable? Whatever it happens to be. And we want to then use what we know about statistics, what we know about the data, what we know about the world, to try to come up with a theoretical distribution for what's going on there. So, for example, we might say something like, okay, the average of this variable follows a normal distribution with a certain mean and a certain standard deviation. Right? And these are theoretical means and standard deviations. They are the true means and standard deviations that describe how this variable changes from one sample to the next, right? Because what we're trying to describe here is a sampling distribution, basically. If we were to take some sample of data from the world over and over and over again, we would get a different answer each time. This is the frustrating and infuriating thing about statistics. We don't just get one answer, we get multiple answers, and the answer is going to change every time we go back to get a different set of data. However, if we are smart about it, we can think ahead of time about what is the distribution that should follow. As I go from sample to sample to sample, I'm going to get different values. But if I plot out a density distribution, like we did in the last video, of what all those different values are, what would that density distribution look like? Right? And if I can think about that properly, if I can write down properly what that density distribution is, then I have understood what my theoretical distribution is. Right? So, for example, let's say that we have a coin that is fair, a fair coin that is heads half of the time and tails half of the time. Okay. And I tell you that I'm going to flip two coins and see what I get. Now we can think about what the theoretical distribution of this variable is going to be. The variable being, what are my observations of coins? Well, I can tell you that, half of the time I'm going to get a heads and a tails in some order. 25% of the time I'm going to get two heads, and 25% of the time I'm going to get two tails. That is the theoretical distribution. Based on what I think I know about the world, I think that this coin is fair, and I'm pretty sure that I can use the binomial distribution to describe the sampling distribution of the coin flips. Then that is the distribution that I should see. If I were to resample the data over and over and over again, flip two coins over here, flip two coins over there, flip two coins up here, flip two coins down here, and look at the distribution across all my different samples, I should get, half the time I get a heads and a tails, 25% of the time I get two heads, 25% of the time I get two tails. Right? That's what I should get. Now, that is the theoretical distribution. And I mentioned the binomial distribution. That is just one kind of theoretical distribution that we know about, right? Theoretical distribution does not have to be about coin flips. It's going to be different depending on the kind of thing that we are describing. So, for example, if we are taking an average of a bunch of stuff, that will typically follow a normal distribution. Let's say I want to look at, what's the average height of a classroom full of students? And I go to this classroom over here, I take the average height, I go to this classroom over here, I take the average height, I go to this classroom over here, I take the average height, and then I plot those average heights all out over and over and over again. I should get something that looks like a normal distribution, because one of the things that the normal distribution does is it describes the distribution of averages. That's one of the things that it tends to pop up in. But of course, there are many other distributions as well. There's the normal distribution, as I mentioned. There's the log normal distribution, which is a variable that is normally distributed after you take the logarithm of it. There's the Poisson distribution for count data, if you just think how often something happens. I mentioned the binomial distribution. There's other ones. There's the gamma distribution. There's lots and lots and lots of distributions. go read a statistics textbook. The point is that we have some sort of theoretical distribution that we think describes how this data that we are getting should vary from sample to sample. Great. Okay. Under the assumptions that we have made about the world, how we think the world works, then we have an idea about how we think the data is going to be distributed across a bunch of different samples. Great. Problem is, we don't have a bunch of different samples. We just have one sample, the sample that we did collect, and that's the data that we have. And our goal is to try to learn something about the theoretical distribution using the actual data that we have. Why do we want to do that? Well, because usually the theoretical distribution has information that we are interested in, right? If I want to know what the average height of a classroom is, well, the average height, the actual true average height of all classrooms is going to be a factor in that theoretical distribution, right? The theoretical distribution of the height of a classroom is going to have at its center, its central tendency is going to be the actual true overall average height of a classroom, okay? So if I can learn about that theoretical distribution, it will then be me learning about the true parameter that I am perhaps interested in. And this doesn't just go for the average height, it could also go for the true effect of X on Y, which is going to be important once we start getting to causal inference. So that's our goal. We have our one data set, and we're going to try to use that one data set to learn something about the theoretical distribution that describes how all the data sets would look if we happen to have a bunch of data sets. So how is this possible? How is it possible we can sort of make that jump? And the way that I want you to think about this is this. We are trying to think about all the possible theoretical distributions, right? It's not just one, right? We don't necessarily know what the average height is of a classroom, right? If I said the average height is 4 foot tall for 10-year-old students. I don't know. Well, if I knew that for sure, then I could very easily construct for you the theoretical distribution. Okay, but I actually don't know that it's 4 foot tall. Maybe it's 3'7". Maybe it is 4'9". Maybe I haven't met enough 10-year-old kids and actually they're all 6 feet tall. I don't know, right? But the goal is I should be able to look at my data, and I can't necessarily know the truth, but I should be able to, rule out or at least say that that they're very unlikely for certain truths. If I got a sample of average classroom heights and it was, 3'7", it's pretty unlikely that the truth is 6 foot tall, right? That's pretty unlikely, which means that I could probably rule out the theoretical distribution that has 6 foot tall as its central tendency. I could say that's very unlikely. That's my goal here. I'm not trying to pin down what the true theoretical distribution is, but I'm trying to use what I know to sort of narrow the range of what I think is reasonable. That's what I want to do. And there's two main ways you can think about this. You can think about the way the Bayesians deal with this, which is that they get data and they think, well, the data that I see is really far off from what I thought it was in the first place, so I should update what I thought about the world in the direction of the data. Or you could go the hypothesis testing route, the frequentist route, which is where you say, based on this theoretical distribution, the data that I see is super unlikely, therefore I will reject the original value. I'm going to talk a bit more about the second approach, simply because it is something that you will see more often, but the Bayesian approach I think is very valuable here, and it's worth looking into, but I'm not going to talk about it. I can recommend maybe you go read some of the work of Andrew Gelman. He's got a couple good books. Regression and Other Stories is a good one. Maybe check it out. So let's walk through a quick example about how this works. Let's again go back to coin flipping, but let's use more coin flips. So let's say that you're going to flip 100 coins, and we want to know, is this actually a fair coin, right? So we think our theoretical presupposition is that the coin is going to be heads half the time and tails half the time. Now, based on that assumption, I can tell you exactly what the theoretical distribution is going to be, because if you flip 100 coins and it's exactly heads half the time and exactly tails half the time, I can tell you precisely based on my probabilistic calculations. I can just use the binomial distribution because I know as a statistician that a bunch of coin flips follows a binomial distribution, and I can show for you what the distribution is. So here I've got a histogram of how often each of the different numbers of heads should pop up if I flip 100 coins. And you can see, right, the most common is 50, but it's not necessarily going to be 50 all the time. Just if I got 49, that wouldn't make me think, well, there's no way that it's 50, right? If I happen to get 49 heads instead of 50. But you can see what's going on here. This is our theoretical distribution, right? Under the assumptions that we have, that we are trying to think about, are these assumptions reasonable? This literally is how the data would be distributed from sample to sample. Now, let's say that we have exactly one data set. We happen to flip 100 coins exactly, and we got 40 heads. 40 is quite far from 50, but sometimes it would happen. Sometimes you would get 40 heads after flipping 100 coins. Sometimes you get 100 heads. Could happen. But the question is, what can this one data set teach us about the theoretical distribution? Well, based on this theoretical distribution, I can now shade in how likely it would be to get 40 heads if in fact the truth was 50. And in fact, I won't just shade in 40 heads, I'll shade in 40 heads or less. Right? This is how likely it would be to get as low as 40 or even lower if indeed the truth was 50. So I can tell you that the area that I have shaded there, that is 2.8% of the distribution, right? That's telling us that there's a 2.8% probability that if this was indeed the theoretical distribution we were looking at, there's a 2.8% chance that we would have gotten 40 or lower anyway. Now, how can we take this information? How can we use what we have observed to learn something about the theoretical distribution? And what we might say is that, well, 2.8% is pretty low. And if we see this data, there's really two possibilities. Either there was something wrong in our original theoretical distribution that we're looking at, right? Either this isn't really the true theoretical distribution, or just something unlikely happens. Something unlikely can happen all the time. And we're saying that this unlikely thing had a 2.8% probability chance of happening. Now, if you're doing a hypothesis test, you would at some point say that of these two possibilities, as this probability gets lower and lower, as the possibility that under this truth, this would have occurred is so tiny that there's no chance it's this anymore. It must be that the theoretical distribution was wrong. And I can then reject that theoretical distribution. Right? That's the idea here, that we're saying this is a theoretical distribution we are considering. If the probability that we got this data under that distribution is small enough, we're going to say, that's probably not right anymore. And in doing so, we've rejected that. We'd say this is not a fair coin. And we have narrowed the range of possible true theoretical distributions that we have. We don't necessarily know that it's like truly 40%. Not 40% heads, maybe, but also, it could be a lot of other things, right? We just know that it's not 50% anymore. At least we think it's very unlikely that it's 50%. Now, in technical terms, what we're looking at is a p-value. This 2.8% is the probability of getting the value that we got or something more extreme, assuming that the sampling distribution, the theoretical distribution we're looking at, is the correct one. Right. Commonly, you might look at a two-tailed test where you're not just looking at is it as far away or more in the same direction. You're looking in either direction. So here I've shaded in both 40 and below and 60 and above. This is 5.7%. And so again, we would be asking, we've ended somewhere in these tails, right? Either these aren't really the tails. Maybe the distribution should be centered over them, right? We have the wrong theoretical distribution. We should move that distribution. Or just something unlikely happened. We happen to end up in the tails. One of those two things happened. A hypothesis test would say if the p-value, the probability of being this far in the tails, is low enough, is lower than some cutoff value we've set, then we are going to decide to come to the conclusion, we have the wrong theoretical distribution. Let's move that distribution somewhere else. Or rather, just consider that it's something else besides this. So again, all we're doing is we are narrowing the range of possible theoretical distributions that we can consider. And in doing so, we are making an inference about what the truth is based on our one sample that we happen to observe. And hopefully we didn't just end up in the tails and mistakenly say that we have the wrong distribution. All right, that's it for describing of single variables. And in the next set of videos, we're going to be talking about how to describe the relationship between variables. And hopefully that will be interesting for you. All right, thank you very much.